All right, hey, welcome back. Hope everybody's Thanksgiving was pretty good, or at least uneventful. It's only been a week. It feels like a long time, I suppose. You should have all got your test results back. If you didn't, let me know. Email me, message me. So here, chapter 10, which is exponents and logarithms. So we'll start with exponents, which really aren't that bad in terms of what we're going to do with them. What I'd like to do, I want to keep this particular video here brief. One main goal, and that is to graph this. Y equals 2 to the power of x. And this is the prototypical, this is the classic example of an exponential function, And you want to, I think this is important to graph it by hand, and I don't want to sound too old school, but if you could get a piece of graph paper and do what I'm about to do, I think it's really helpful to develop an intuition about how these functions work. It's not complicated. You don't want to make it worse than it is. So let's go ahead and make a graph. Remember, like I said before, how do you make a graph when you don't know how to make a graph? Plot points. Again, it's not very insightful. It may seem a rather crude technique. Nonetheless, I want to say it works. You could be misled, but you're not going to be misled in the context that we're in. So suppose x is equal to 0. What's 2 to the power of 0? Well, we spent quite a bit of time on that, and that's 1. What's 2 to the power of 1? Say that's 1 over, and there's 1 up, 2, 3, 4, 5, 6, 7, 8. If we're over 1, we're up 2. Because just put a 1 in for x. 2 to the 1 is 2. See, it really is that simple. Not too bad. Let's go over 2. 2 to the power of 2. 2 times 2 is 4. So we'll go 1, 2, 3, 4. If we go over 3, 2 to the power of 3. 2 times 2 times 2 is 8. And things get difficult at this point. At least looking at the equipment that I have here, if x is 4, 2 to the 4th, 2 times 2 is 4, times 2 is 8, times 2 is 16. Well, it would be up in space up here. And if it's 5, it's 32, and 6, 64, 128, 256, 512, 1024, 2040. It gets pretty tough, right? To calculate quickly in your head, but also to graph. Now, we don't want to neglect using negative numbers. What's 2 raised to the power of negative 1? By definition, it's 1 over 2. 2 to the power of, negative 2. It's 1 over 2 squared, which is 1/4. So when x is negative 1, y is 1/2. When x is negative 2, y is 1/4. So what sort of behavior do we get over here? There's negative 1, negative 2, negative 3. 1/2, 1/4, 1/8. And now we'll connect the dots. And that is the graph of y equals 2 to the x. What's the y-intercept? Hey, remember on every graph, you want to try to find the x and y-intercepts. What's the y-intercept? 1. What's the x-intercept? Well, how do we find an x-intercept? We set y equal to 0 and solve for x. 2 to the what power equals 0? Think about it for a minute. 2 raised to the power of what equals 0? That's right, you can't do it. 2 to the 0 is 1. 2 to a negative power is 1 over 2 to a power, positive power. Well, that can never be 0 because the numerator is not 0. So there is no x-intercept. And so what happens out here is this graph gets arbitrarily close to the x-axis. It becomes more and more flat. Now over here, I don't want to have, it's very difficult to draw these graphs and not be misleading. This graph does not become vertical, and it does not adopt vertical-like behavior in really in any way. Now, if you graph this on Desmos and you zoom out and you zoom out, you could be fooled into thinking that it almost becomes vertical, but it doesn't. It goes as far over to the right as you could imagine. I mean, you could make x 100. The thing of it is, you'd be 2 raised to the power of 100 up. And that would be pretty high up. You can imagine how big a number that is. Or 1,000. Or 1,000,000. Nonetheless, it doesn't go as far over to the right as you could possibly imagine. Now, oh, geez, I didn't get fresh colored markers here. Okay, well, you'll have to pretend here for a second. Maybe I'll make it dashed. Suppose I was going to graph y equals 3 to the power of x. Well, how would that differ, or how would that compare to y equals 2 to the x? Well, when x equals 0, we're right here. When x equals 1, we're up at 1, 2, 3. When x equals 2, we're at 3 squared. 3 times 3, we're at 9. We're already up here. Now when y equals 3, we're at 27. I'm already off the board. What if y were to equal -1? 3 to the -1 is 1/3. So we're down here, and then 1/9 and 1 over 27. So here I'll try to do this with a dashed line. Now, if you step back and you take a quick look, these graphs really look the same. They really have the same kind of behavior. This explosive growth over here and this sort of leveling out to flat or to horizontal when we go this direction. Now, it turns out we'll be able to shift these graphs up and down just like we did with parabolas, or just like you could do with any graph. So I was almost going to say to the left of the y-axis, but that's not really, well, it would be to the left of the y-axis if you go far enough, regardless of the situation. But the idea is if you go this direction, the graph levels out. If you go this direction, it increases more and more rapidly. And if we did y equals 4 to the x, 5 to the x, 6 to the x, same thing. What if we graph this? Let's say y equals 1/2 raised to the power of x. Well, when x is 0, we still cross through here. We still keep getting the same y-intercept, because anything to the power of 0 is 1. What if x is 1? Well, we're 1/2, 2, 1/4, 1/8, 1/16. Now, a lot of things, like I keep saying, they go back to fractions amazingly over and over again. What is 1/2 raised to the power of -1? Something you should know, or at least you should be able to do it in your head. But it's 1 over 1/2 raised to the power of 1, which is 2. Basic fractions. So -1, we're up at 2. -2, we're up at 4. And we get, I already did that. Maybe I should have done dashed lines here like this, like that. Now this is the same graph. This is the same graph as this. It's just rotated about the y-axis. In this case, we could also say reflected about the y-axis. But if you took this graph here and you rotated it about the y-axis 180 degrees, well, three-dimensional space, you would get this graph. And that's what I meant in some sense. All the exponential graphs are this right here. Now they may be modified. They may be made steeper or less steep, or rotated about an axis or any other line, or shifted around. But they're really based on this one graph right here. So you want to know, you already saw this here. You want to know this graph here on sight. Just like you know a lion when you see one, or an elephant when you see one, or a giraffe when you see one, or a penguin when you see one. And you wouldn't mistake a penguin for a giraffe, because you're just familiar with them. You just wouldn't make that mistake. And you want to know this. And now here's a thing I want you to contrast it with. Now they're a little bit closer than a giraffe and a penguin. I don't know, maybe a lion and a tiger. In fact, if you don't look too closely, maybe they look pretty similar. So let's compare this with this. We want to compare these two. Now again, we can throw this in the decimals, bam, right away, and you'll see the difference. But I think that if you plot points, you get a better feeling, a better gut feeling for why this is the way it is. It's not complex. You don't want to make this more difficult than it is, and hopefully I'm not doing that. I could be guilty of that sometimes. Let's graph these two. Here, I'll make this one a solid line, and I'll make this one a dashed line or a dotted line. We just graphed this one, but let's do it again. When x is 0, we get 1. What about here? Remember, this was sort of the mother, the basic, the prototypical, the classic example of a parabola, of a polynomial function of degree 2. And this is an exponential function where the base is 2. And it seems, I mean, you know, just to look at it, they look a little bit similar, and they seem to be screaming out for a comparison. Now, excuse me, what about if you put a 0 in there? You get 0. Well, okay. They're not the same, so at least we know that. Let's let x equal 1. Put a 1 in here. There's 1. And what do you get there? You get 2. Put a 1 in here. 2. Geez, 1, 2, 3, 4. Put a 1 in there. You get 2. Put a 1 in there. You get 1. Okay, so they're still different. And you don't want to jump to any false sort of conclusions here, I suppose. Like, you know, if you notice from here to here, it went up 1. From here to here, it went up 1. But that's not going to hold true. These are not linear functions. Put a 2 in here. What do you get? 4. Put a 2 in there. Hey, what do you get? 4. So at 2, they're both at 4. Now, so far, this graph looks like this. And that one looks like that. And as far as the behavior goes, it looks as though the dashed line got off to a slow start, but is caught up to this graph. But if you stop there, you'd be completely wrong. And wrong in sort of a catastrophic way. But let's continue on. Let's put a 3 in there. Now, it may be difficult to graph here, but if I put a 3 here, what's 2 to the power of 3? 2 times 2 times 2. Use my fingers here. 2 times 2 times 2. 2 times 2 is 4. Times 2 is 8. So we're up here at 1, 2, 3, 4, 5, 6, 7, 8. So the solid line, just like we did a minute ago, is up there at 8. What if I put a 3 in here? Well, 3 squared is 9. So I better put this over here. So it looks like, hey, maybe we should use decimals to get a better looking graph, but do this on a piece of graph paper. Just try it by hand, just once, just one time. It won't kill you in your life. Get out a piece of graph paper and try it. And you say, well, look, the dashed line again got off to a slow start, overtook the solid line, and now it's above. But let's try it. X equals 4. What's 2 to the 4th? 2 times 2, 4, 8, 16. Put a 4 in there. What's 4 squared? 16. Hey, wait a minute. They come back together again. Now, this is going to be tough to graph without a piece of graph paper, or maybe I don't have enough room here. But it looks as though what's happened is that the dashed line came up here, caught up to the solid line, and then I'm not going to try to make this look really good. These things are actually, they are tough to graph by hand. I don't graph them by hand all the time, or rarely if ever, but look. And then, here, this is 4, this is 2. They cross at 2, they cross at 4. Now, let's consider what happens when you move beyond that. How about 5? What's 2 to the 5th? 2, 4, 8, 16, 32. What's 5 squared? 25. Well, now the solid line is way ahead of the dashed line. What about a 6? What's 2 to the 6th? 64. What's 6 squared? 36. 64, 36. This is really winning the race. Let's go up to 10. Try 10. What's 2 to the 10th? Try it in your mind. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. What's 10 squared? 100. Well, now this is 900 above this. What if we went up to 20? 2 to the 20th. Which I don't know off the top of my head, and I don't feel like going to, but I think this is over 1 million. What did I just say? 20? Yeah. What's 20 squared? 400. Well, now there's no comparison. In other words, although it's unclear maybe in the small little region here who's going to sort of win this race or grow more rapidly, becomes very clear as soon as you really get to numbers like 5 or 6, that the growth here is much more dramatic and of a different type. And what we're going to say is this has exponential growth. And when people say exponential growth, they use that term a lot. People use it whether or not it's actually the case. This is not exponential growth, although it is rapid growth. I mean, make x 100 was 100 squared, 10,000. It's pretty dramatic. Make x 100. Try throwing that into one of your calculators, and you'll see it's, I don't know what number it is. How would you do a rough approximation of that without a calculator? Well, it wouldn't necessarily be easy, but let's say you have 2 to the power of 100. And I want to know what the order of magnitude. Now, that's a term I haven't used before, but it really means, what are we talking, tens, hundreds? And I'm going to talk very carefully about that. Oh, I did talk about order of magnitude. That's right, in a previous video on the rules of exponents, the laws of exponents. So the order of magnitude is, if you write this in scientific notation, what's the power of 10? First thing that occurs to me is, how about if we just did 2 to the power of 90? And then this is 2 cubed raised to the power of 30. Because rule of exponents, take a number raised to a power, you multiply the powers. And so this is 8 raised to the power of 30. Now this is a dramatic underestimate, so now I'll make a gross overestimate here. Hey, you know what I could have done? Maybe now I think about it. How about 2 to the power of 4? Now what's 2 to the power of 4? Sorry, is 16. Or so 4 times what? 25 is 100. Oh, so hey, even better. Look at this right here. So this is equal to this, and well, it's going to be a really big underestimate here, but 2 to the 16th is, or 2 to the 4th is 16, and so that's greater than 10 to the 25th. So if you put 100 in here for x, you'll get a number which would because really that's 16, not 10. In fact, well, I'll just leave it like that. But 2 to the 10 to the 25th, I mean, how big a number is this? And the answer is really, really big. In fact, it's just not that far off. It's bigger than Avogadro's number, if you know what that is. And if not, we'll talk about that later on. So at any rate, the behavior of this is that although you may get some slow growth at first, it's just tremendous afterwards. But we're going to talk a lot of examples from Moore's law to bacteria in a petri dish. Excuse me, and we'll see the kind of behavior that you can get with this. That's enough for this video, but what we're going to do is we're going to continue on and we're going to cover all of chapter 10. We'll come back to 10.1. 10.1 sometimes gets people confused. We don't need it for a while. Whenever you see this in the book, f of x, if you're familiar with that, great. If that bothers you, cross it out and use the letter y. It means exactly the same thing, or at least for our purposes, exactly the same thing. Okay, so hey, that's enough for now.